ETM 330 Lab Final Temperature Control System. So my name is Michael Aleda. I was working with Jacob Wierschmer and Michael Bavara. They helped me a lot building the circuitry for the control system. So they helped me pick out the resistors for the supply that we chose, and they had helped me build the sensors previously in class, and they definitely played a big role in building these circuits. So this circuit here is my heating circuit, and I had my sensor going across, and I have it plugged in right under the resistor there. So this circuit has a PWM coming from the myria, and it's actually run off of a 9-volt battery, and we chose the resistors accordingly to get the right power that we wanted. And then on this side we have two separate circuits for the sensors. One which is connected to our silicone sensor in the straw, and then one where there's just the ambient sensor sitting right there. So I actually did, they're both connected to the same power source, splitting it evenly, and they're sharing a 9-volt battery, which causes them to have 4.5 volts each, very close to 5. So it happened to work out pretty well. So that's kind of an overview of the circuitry that we're using. And now I'll move on to the LabVIEW program. So for the LabVIEW program, I have my two analog inputs of my ambient sensor and my heater sensor. So when they come in, they are a small value of millivolts, so around 600 to 650 millivolts. So I actually multiplied them by 1,000 and rounded them, so I'm strictly working with millivolts to round off some of the unnecessary decimals. So from there I have, this is the voltage, then here's the millivolts that I read out here. So then I have those going in. I also have the waveform for both of the sensors, which you'll see up top here once the program is running. And then I have a command offset, which I put in for -10, because when the temperature goes up, the voltage goes down. So I'm simulating that the ambient temperature is 10 degrees higher, or a voltage that creates an offset of 10 millivolts. So that's going to go into my error, and that's going to go into basically that's basically the input, and how I want the heater to make the other one match that. So I subtract the two voltages to get the error, and I have the error over here. So you can see right here it's -1, so that was at a state where the system had somewhat stabilized. So I have it so that the error, which I mostly found that when I heat it up with my fingers, that the error would be between 0 and 18 millivolts. So I divided that by 20 to give my duty cycle. So as at the highest of like a offset of 20, a difference of 20, an error of 20, I get 100% duty cycle. And as it comes closer to an error of 0, my duty cycle gets closer to 0. So that duty cycle goes into my PWM, which is connected to my circuit. And now I will demonstrate how it is able to stabilize the differences between the ambient with the offset and the temperature control, the heated sensor. So now we're going to test the feedback of the system. So you can see that my sensors are both at about 630 millivolts, which would mean that my error would be 0, except that I set a command offset. So that's similar to if someone went up to a thermostat and wanted to raise the temperature. That's like them raising the temperature, because it's an inverse function between the temperature and the millivoltage. So my error is actually 16. So what's going to happen is when I input the resistor, it's going to try to eliminate this error, and it is going to try to get the error to 0. So I have it proportionally set so that the duty cycle is equal to the error times 1/20. So this only works for a range, well, it can work for a larger range, because when the duty cycle is above 1, it just works as a duty cycle of 1, so it'll still be heating it. So right now I'm going to input the resistor, the heater, and then we'll start to see the air go down. And as the air goes down, the duty cycle will go down. So when the air gets to 0, the duty cycle will also be 0, and it should help it to stabilize. So just pop this guy in. And now you can see, watch the air in the duty cycle. So this graph is also showing the air as it goes down, and you can see the duty cycle going down with it. So the air has already dropped from 15 down to 11, down to 9. At 9, my duty cycle is 0.45. Now at 7, it's 0.35. Now the air is down to 4, so my duty cycle is only 0.2. So it's a proportional of air times 1/20 equals the duty cycle. So this only works for a heater. Doesn't work as cooling because I don't have any cooling system. But you can see that the air is now getting down to 2. The duty cycle is 0.1, 10%. Now the air is making it down to 1. And you can see that my ambient sensor is still around a little bit larger, a little bit hotter than it was at 630, but the heated sensor is a lot hotter as its millivoltage has dropped. So now you can see the air is getting down to 0 and the system is beginning to stabilize. So that kind of sums up how the control system works. I was not able to use an integrator. I may have done it a little differently than the professor, but it works. I was able to adjust the PWM according to the air, and now that the air is 0, the PWM is 0, and it's able to stabilize.